Oh, hello, everyone. So I will instead present for Dr. Wei Yu for the talk AI GPU workflow for unconventional fracture reservoir simulation. So first, I want to give a background regarding the overall unconventional industry. So regarding the unconventional, we're mainly talking about shale gas and shale oil, tight oil reservoirs. So but in total, there are about 1 million oil and gas wells in the United States. This is including everything. Okay, so however, there are only about 200,000 shale gas and tight oil wells. However, if we look at the numbers from the EIA, they are contributing to more than 50%, actually 70 to 80% of the total hydrocarbon recoveries. And regarding the drilling rigs, there's also a lot of these for the unconventional reservoirs. So for shale oil reservoirs, for example, the Eagle Ford, Bakken, in total there are about 400, more than 400 rigs, drilling rigs for the shale or tight oil reservoirs. For the shale gas reservoirs, mainly they are distributed around the Haynesville and also the Marcellus, which is about more than 100 rigs for the shale gas. So we see a big contribution from these unconventional reservoirs. And when we are talking about unconventional reservoirs, we must talk about the hydraulic fractures. So for the hydraulic fractures, when we are pumping fluid and sands into the reservoirs, we create these man-made hydraulic fractures. And here we want to define like two phases for the hydraulic fractures. So the first phase is called the wetted fracture geometry. So this is when you put all the pumping fluid, all the proppants into the reservoir. And this is when you initially frac the reservoir and do the completion job. Usually this kind of wetted fracture geometry is kind of, the number is large. For example, the length and height can reach all the way up to hundreds of meters. And for the height, it can also reach really high number, like 100, 200 feet, usually in the Eagle Ford. However, if you put the well on production, because of the changes in the effective stress, not all of the fracture geometry will actually contribute to the production. So this is the second, what we call the second phase for the fracture geometry, or you can call it effective fracture geometry. So here we can see here in this schematics, some of the papers say that this kind of proppant distribution along the fracture is uniform, meaning they can reach all the way to the tips of the wetted fracture geometry. But however, in reality, this is not true. Only part of the fracture will have a higher concentration of the proppants, and the rest of them either have very low concentration or they got crushed by the effective stress changes. And it's actually quantifying these effective fracture, the number of these effective fracture for the effective half length and height. This is the most important thing that we need to consider when we want to do like design optimization, such as the optimal well spacing and also the completion designs. Okay, so here's some of the literature review regarding how we can understand these fracture geometry better. For example, in the HFTS, where we have a lot of fiber optics data, such as the low frequency DAS data for the wetted fracture, and also the DSS, which is the distributed strain sensing for the effective fracture geometry. These are quite popular technologies to help understand what is the areal extent of these fractures. And also, there are some also hybrid approach using both the fiber optics and also the pressure gauges. You need to put more than, of course, more than one pressure gauge because you need to measure along the wellbore, both horizontally and vertically. So each of the pressure gauge is about 20,000 USD, which is quite expensive. And if you put more than 30, you can imagine the investment here is big. However, a lot of operators are still trying to better understand the fracture geometry. And they found out actually that the effective fracture half length is about 30% to 50% in this ballpark of the total wetted fracture half length. Okay, so this is another study in the Permian Reservoir. So we see that the hydraulic fracture using the fiber data, they measured that to be about 700 feet from this paper. You can see these fiber measurements. And using both combination of the DSS and also the pressure gauge data, they found out that after 1 week or 2 months of production, the effective fracture reduces to from 700 to the 600 feet, and all the way up to 300 feet. And you can see that different completion designs, they follow a different so-called degradation trends. And so this is a very interesting observation from the field, and they try to use these kind of data to optimize their frac designs. So that brings us to the AI GPU workflow for the fracture simulation and also reservoir simulation. And I think Dr. Miao already went over these. So for this workflow, we are able to integrate from the patrol model and also the geomechanics model. We can directly import those, consider the geomechanics data, and we input into our software interface to run the ZFRAC simulation to quantify what is the wetted fracture half length and height. And then we go to the EDFM with the GPU simulator. It's all the EDFM AI as I showed in the demo to quantify the effective fracture geometry. Yeah, so I think Dr. Mel also showed this slide, but I want to go into a little bit more detail about our hydraulic fracture simulator ZFRAC. So the ZFRAC is based on the boundary element method. And we currently we are supporting the parallel computing using multiple cores. So each stage simulation is about 10 seconds or less than that. Because of this efficiency advantage, we are able to develop a real-time hydraulic fracture simulation, which you can see here. This is a TFOC as Dr. Mel mentioned. And as the pumping data is transferred back into this cloud platform, all of these are cloud platform that we work with an operator to develop this. And using our ZFRAC model, we can seamlessly integrate the fracture geometry along with the pumping pressure. So you can actually see what natural fracture are activated, and also you can better evaluate the fracture hits risks regarding any well's completion job. And then for the fracture propagation model, we are also able to couple the AI algorithm to automatically calibrate the pumping pressure of any completion stage. And using these kind of data, we are able to calibrate the hydraulic fracture propagation model through tuning uncertainty parameters. A lot of times for the 3D geomechanics data, especially the minimum stress, there's a very high uncertainty associated with that data, because you only have the when you are building a model, you only have the vertical well, but you are interpolating between different wells. So the SH mean is actually a big factor that we consider to calibrate as an uncertainty parameters. And also there are other parameters such as the whole number, the erosion effect of erosion, and also the friction parameters that we can consider for this workflow. And then after we calibrate the hydraulic fracture model, we need to evaluate the production potential using the reservoir simulation. So we already talked a lot about the EDFM model, so I won't go into the details regarding that. But for the EDFM model, we currently can support the import of 3D geological model and directly transfer those kind of complex fracture boundary from the ZFRAC into the GPU reservoir simulator. And then we perform the automatic history matching for the reservoir model calibration. So here we actually over the years tried and experimented with all kinds of AI proxy model for the optimization. For example, we tried the polynomial, we tried the KNN, we tried the neural network, we also tried the XGBoost, and finally we found out that for the AI calibration, is actually there's an algorithm called ESMDA, which is an ensemble smoother that can help you consider a large number of uncertainty parameters. Like it works really good with even more than 100 uncertainty parameters. So imagine if you are doing a lot of wells and you need to calibrate a lot of uncertainty parameters. This ESMDA algorithm is really good regarding the automatic history matching. And we are also coupling with powerful GPU with GPU reservoir simulator to consider the effective fracture geometry here. And for the EDFM AI here, one new functionality we are able to consider is using multiple GPU supercomputing bundled together to help us enlarge the model size so we can consider, and also speed up the simulation efficiency drastically. So as we know that there are a lot of cloud platforms that allows you to rent like powerful GPU like H100 and V100 series. So those are like industrial level GPU, much more powerful than the desktop, like such as the NVIDIA 1590. So we are able to work with the one of the cloud GPU provider, and we are able to couple the EDFM AI with these multiple GPU bundles to help us better consider tens or hundreds of wells at the same time. And a recent feature that we just developed, and also we are still trying to improve, is the fracture degradation. So you can see here the fracture geometry when we initially frac it, the effective geometry maybe at the very beginning is like large, but when the production continues, the fracture degrades with time. And you can see here, actually, this is a degradation based on the proppant concentration. So we are currently also working on improving the ZFRAC model to better quantify what is the proppant concentration distributed in the hydraulic fractures. Okay, so just to give an example, so this is one of the cases that we run before. So for this scenario, we are running the ZFRAC AI for hydraulic fracture model calibration. So here we're able to run 4 iterations of AI optimization, and each iteration runs about 10 ZFRAC cases. So we repeated this for more than 60 stages, totally about 2,500 cases. And for the average CPU time for each stage is about 10 seconds. And as I know, some of the other commercial simulator, this number is impossible. They need to run at least like more than 5 minutes for one stage. So imagine running this more than 2,000 cases, it will take forever. And we also considered some of the key erosion and friction parameters regarding all these 64 stages. And we are able to calibrate the pumping pressure pretty good. So this is the final calibrated fracture geometry across all the 3 wells. And here we are able to calibrate for each cluster what is the wetted fracture length and also the fracture height across all the 3 wells. So the average value for the half length for the wetted geometry here in this pad is about 120 meters and fracture height is about 20 meters. Then we directly integrate these fracture geometries into the reservoir simulation calibration. So here we actually run more iterations, 7 iterations in total, and we run initial iteration 50 runs and all the other iterations 25 runs, so 200 cases of reservoir simulation. With 8 years of production history, each case we are able to finish just in 2 minutes. And the entire calibration time for all these 200 cases only about 6 hours. And we consider key parameters such as the permeability, the half length, and also the effective height, and also some other uncertainties. And these are the results that we got from the ether matching. We have the gas flow rate as a constraint. We are able to match the bottom hole pressure and water flow. So this is also the same the plot I showed during the demo. So you can see here all these these lines, the purple lines, representing the initial fracture geometry. And when after we calibrated these reservoir models, we found out that only about 50% to 65% of the length direction is actually contributing to production, and about 50 to 80% of the height direction is effective. And when we compare this AI GPU powered workflow with the traditional CPU workflow, and if we consider a 10 million grid number model, usually this or GPU AI workflow is able to finish just in about a week if we scale up this reservoir model to about 10 million grid blocks. And for the conventional workflow, for 10 million grid blocks for even a single simulation run, I believe it would take several days to finish that. And the efficiency gain by our GPU AI workflow is can reach about 100 times. This is including the base case running and also the calibration run. And a lot of times we will also need field experience and engineering experience to successfully perform those calibrations steps. And for the cost, we are able to decrease per well calibration cost about 10 times. And then I want to talk about a new technology, which is fracture degradation that we developed in the EDFN module. So I think Dr. May also put this slide. One of the details regarding the fracture degradation is that using traditional way of static fracture geometry, for some of the scenarios, some of the cases, it's super difficult to obtain a good match, especially if your production history is quite long, spanning several years. You can see here, we actually experimented in a tight oil reservoir with different fracture geometry, but they are all static, meaning the geometry doesn't change along with time. And you can see that here the pressure match, they either overestimate the pressure in the beginning, or they can match the beginning, but the later time period it's quite difficult to match. The pressure shoots up. Or using a small geometry, the late period is fine, but the initial match is not good. Okay, so using this fracture degradation feature, we are able to consider the change in the fracture geometry. So you can see initially we have this size of fracture geometry. Oh, sorry. And as the time goes on, this fracture closes. So using this kind of dynamic geometry changes, we are able to much better match the pressure response. And we actually apply this new technology into the one of the real case in the for the tight oil wells in the Bakken. So you can see here, this is we have a collaboration with one company, and they have two pads, and this is one of their pads that has 13 wells in this reservoir. And we were able to by the first time to capture all these fracture degradation, the change of the fracture geometry, closure physics. And we are able to also match all those 13 wells production response pretty good. And one interesting observation here is that when we look at the fracture degradation in both the height direction and also the length direction, we see that the fracture length degrade much more quickly, and it reduced to much smaller value compared to the initial geometry for the half length direction. But for the height direction, it doesn't close that much compared to the half length. And we also look at some of the literature in the Bakken, and this is quite consistent with literature work. They use this both the pressure gauge and also fiber data to calibrate these. And the results, our results, kind of consistent with literature findings. And another application here is for cube development. So for some part of the world, the unconventional play, they have a really big vertical span of the reservoir, like the pay thickness is really big, can reach all the way to 1,000 feet. So in order to tap all these unconventional resources, a lot of operators are developing this so-called multi-layer strategy to drain more efficiently from the whole reservoir azole. So this is also another real reservoir that we apply to. This is a shale gas reservoir, and we were able to model a 6-layer development using the ZFRAC with about 20 wells in total in this pad. And we also did a lot of work. I didn't have the time to show all the details regarding this, but we also did a lot of sensitivity regarding different horizontal spacing and vertical spacing regarding this reservoir. And for the fracture simulation for this reservoir, with 20 wells and more than several hundred stages, we are able to finish the simulation in only 2.5 hours. And for the GPU reservoir simulation, we only take about 7 minutes to model this 12 million grid blocks. And finally, I want to also talk about the gas EOR in the shale oil reservoirs. So this is one of our earlier work using the EDFM to model the gas EOR in the Eagle Ford. So we were able to model more than about 10 wells and also put different fracture geometries along the wellbore. And we also considered some of the fracture heat phenomena regarding the EOR in the shale oil reservoir. And the thing here I want to talk about is that using the EDFM with the GPU reservoir simulation, we should be able to consider more wells, both vertically, laterally, and also the horizontally and also the vertically. Yeah, so this is the EOR if the incremental recovery from the EOR that we modeled. So we are able to, for this reservoir, we were able to get a EOR increase of more than 20% regarding the Eagle Ford gas EOR. Okay, so just to wrap up, so this revolutionary AI GPU driven geology engineering workflow, using this workflow, we are able to quantify hydraulic fracture and effective fracture, considering the complex geology model, geomechanics model, and also natural fractures within a highly reasonable time frame. And the second point is that using the AI-guided calibration tools for both ZFRAC and EDFM, we were able to obtain not only a single realization models, we are able to capture a lot of these variations in the uncertainties with multiple wells and help us better evaluate the completion design, evaluate the gas EOR, and try to optimize those designs. And for the new workflow, the calibration is highly efficient. It takes less than 1 week, which using the conventional workflow, it might take more than several months to finish compared to the traditional simulation workflow. And thank you for listening to my talk. And now I welcome any questions and comments.